This lecture is about how to calculate the pH of weak acids and weak bases, which requires an ice table. In the last PowerPoint, we talked about how easy it is to calculate the pH from strong acids and strong bases because 100% of the original strong acid or base dissociates. And so simply by taking the log of the concentration of the original acid, we can get pH, okay, because these two equal each other. Well, in a weak acid or weak base, much less than 100% of the original acid dissociates to form the individual hydronium ion and conjugate base. And the question is, depending on the weak acid, how much of the hydronium ion is formed? How much of that original weak acid dissociates to make hydronium ion? That's going to determine the pH. So we have to do an ice table so that we can calculate the equilibrium concentration of the hydronium ion. So again, just kind of backing up to strong acids and strong bases like hydrochloric acid. If I were to put 100 molecules of HCl into water, all 100 of those molecules would transform themselves, completely dissociate into the hydronium ion. And so the pH could be simply found by taking the minus log of the original concentration, 0.050, for a weak acid. Similarly, for a strong base, and just a reminder here, make sure you memorize the strong acids and strong bases. Barium hydroxide is one of the strong bases, and I threw this example in so that you don't forget about stoichiometry. So barium hydroxide, when we put it in water, 100% dissociates into the cation and the anion, which for a base is hydroxide, for a strong base is hydroxide. But note that barium, since it has a 2+ charge as an ion, is going to have two hydroxides. And so when you write out the ionization reaction, make sure you account for those two hydroxides. And when calculating pH, well, originally a hydroxide ion concentration, make sure you account for the stoichiometry here, right? For every 1 barium hydroxide you dissolve in water, you get 2 hydroxides, okay? So the concentration of hydroxide is going to be 2 times whatever the original concentration of barium hydroxide was. I kind of got off track a minute, but just wanted to remind you that for some of the bases have more than 1 hydroxide. Actually, some of the acids do too. So let's move on to how do we calculate the pH of a weak acid or a weak base. So again, looking at the generic chemical equation for a weak acid, it is in equilibrium. And the question is, how much product does this particular weak acid form? Because that's going to determine how much hydronium ion we have in solution and ultimately what the pH is going to be. So for all weak acids, the Ka, A stands for acid, which I guess is probably obvious. For all weak acids and bases, the K is much less than 1. Here's a sample problem. In this case, they gave you the pH. Now, one thing that I want to point out, please jot this down and make a note of it. It tends to kind of slip by the minds of many students, and it's critical to being able to solve these problems. Anytime you are given pH in a problem, that represents the equilibrium concentration of hydronium ion. So they're giving you a gift for your ice table, okay? So make sure you jot that down. So here's the particular equation that we are talking about. It's acetic acid. No, it's formic acid, sorry. Now, let me just say here too, you don't even have to know the formula for any weak acid. You could just continue to call it HA and you're going to get the right answer, all right? If you notice as we go through these problems, knowing the formula of the weak acid has nothing to do with solving the problem. All right, so here's the chemical equation. Here's the expression for Ka, right? Products over reactants. Remember to leave water out of all of these. It is a liquid. Concentration does not change. All right, so in our ice table, we make use of the pH value they gave us. If you look back in that question, they said that pH equals 2.38. And so finding the equilibrium hydronium ion concentration from that, we go back to our reverse equation using pH itself for hydronium ion. And we now have the equilibrium hydronium ion concentration, which gets plugged into the ice table. And since at the beginning of the problem there was zero product, then we can, now that we know the equilibrium concentration of hydronium ion, we know what the change was, right? And whenever you know the change, that means you automatically know the change for all the substances in the reaction. So since this reaction is 1-to-1 stoichiometry, that means the change that we just found for hydronium ion is the same for all of the substances. Now remember to put a minus sign in front of the one reactant because that concentration is decreasing. Now we can calculate the equilibrium concentrations of every substance. Notice that we do not have to use X in this ice table, which makes it a lot easier. Anytime you know the initial and final concentration of any substance in an equilibrium, you don't have to use X, okay? Now, plugging the equilibrium concentrations back into the expression for the equilibrium, we get that the Ka for formic acid is 1.8 times 10 to the minus 4. Not hard. So hopefully you've done enough ice tables that are beginning to seem somewhat routine to you now. Let's shake up the wording of the problem. This is still working with a weak acid and setting up an ice table, but do you remember the one we just did? They gave us the pH and they asked us to find Ka. What if it's the other way around, okay? What if they give us the Ka and ask us to find pH? So you'll see we're going to have to use X in this one. So here's acetic acid. Again, you could just as easily call that HA and A minus and still get the right answer. So the equilibrium constant expression, and again, you could just as easily write this using my generic A terms and still get the right answer. Alrighty, so here's the ice table. Let's look at how to set that up. We were given the initial concentration of acetic acid, which pretty much is always the case. You assume the concentration of the products are 0 unless you're told otherwise. And we have to use X, right? Because we don't know any final concentrations. So here we go. And originally we would say 0.3 minus X would be the equilibrium concentration of the acetic acid. Now, the big question is, can we neglect this X so we don't have to go through the hassle of a quadratic equation? Well, my rule of thumb is that if the K value is on the order of 10 to the minus 3 or smaller, so 10 to the minus 4, 10 to the minus 5, etc., it is usually safe to neglect X. So this looks like we're in the realm of being able to neglect X. So let's go ahead and do that, and it will greatly simplify our problem. So plug the equilibrium values into the expression for Ka, and of course we neglected X. It's very easy now to solve for X. And we find the X, which represents concentration of hydronium ion, is here. Now be careful, go back and read the question always, because it didn't just ask for the concentration of hydronium ion, it asked for the pH. So we have to do one more step, minus log of the concentration of hydronium ion, and the pH is 2.64, which is about what you would expect for an acidic solution. percent ionization is a common term you will come across when dealing with weak acids and weak bases. It's basically telling you what percent of the original weak acid, which is HA, that's our original weak acid, what percent of it actually ionized. And so, as any percent, right, it's the ratio of part over whole, which is how much hydronium ion is present in the solution compared to what was the original concentration of the weak acid. And then because it's a percent, multiplying it by 100. For example, let's take formic acid. That is a weak acid, and let's say the original concentration was 0.1 molar. If we found that the concentration of hydronium ion present in solution was 4.2 times 10 to the minus 3, the percent ionization, again, it's smaller over larger, part over whole, times 100, 4.2%. Now, the percent ionization of most weak acids and bases is really, really small, like usually hovering around 1%. So, here's a sample problem. Calculate the fraction. Now, fraction's not percent, right? It's just the ratio without multiplying by 100. Starting with 0.5 molar. This is what's in bleach, hypochlorite acid. It kind of looks like a base because it starts with OH, but it's not. It actually loses an acidic hydrogen. All right, so setting up a typical ice table. And so you start it the same way, but remember what we're looking for is we're looking for the fraction ionized, which would be concentration of hydronium ion over the original concentration. Now, original concentration of hypochlorite, okay, not the equilibrium, that's the original. All right, so, but this Y, I'm using Y instead of X here, looks safe to neglect because the K value is quite small. So plugging in the values and neglecting Y because K is very small, solving for Y, which is the hydronium ion concentration, 1.4 times 10 to the minus 4. The original concentration of the hypochlorite is 0.5, and interesting, it said fraction, not percent. Well, if you want to get fraction, you would not multiply by 100. How's that? We can also switch the wording up with a problem that involves percent ionization. So in this case, you are given the percent ionization and asked to find the equilibrium constant. And so the first thing that you want to do is use the percent ionization given to find the concentration of hydronium ion. So again, that's just remembering the formula for percent ionization. It is the concentration of hydronium ion divided by the initial concentration of weak acid added to the solution. And then we can isolate and solve for the concentration of hydronium ion, in this case, 0.00925 mole. Once we have the concentration of hydronium ion, realize that that also equals the concentration of the conjugate base because they're formed in a 1-to-1 ratio, and that the equilibrium concentration of hydrogen fluoride is the initial concentration, which they told us was 0.250 molar, minus concentration of hydronium ion you just found. So the equilibrium concentration of hydrogen fluoride, we can find that, and therefore now we can plug everything we have into the expression for the equilibrium concentration, or the equilibrium constant. And there we have it. I want to do at least one problem that involves a weak base. We don't do enough of those as examples, and I don't want that to throw you off on the exam. So let's just say a weak base, any weak base. Again, you don't need to know the exact formula of either the weak acid or weak base. You still get the right answer. But remember that when you have a base, when you drop a base in water, you're going to produce hydroxide as your ion, not hydronium ion. So keep that in mind. So here's an example for us to walk through. What is the pH of methylamine? Again, you don't need to know what the formula for methylamine. You can just call it a B if you want. And also a reminder here that any nitrogen-containing compound that's neutral overall is likely to function as a weak base. And here's the Kb value. Just kind of heads up, I'll try to remember to mention a couple other times, but every now and then on the standardized test, not me, instead of giving you Kb when you're dealing with a weak base, they may give you Ka. So please remember the relationship between Ka and Kb in case you need to calculate it. So if they gave you Ka, you would have to use this formula and calculate Kb before you could work a base problem out. Alrighty, so setting up the ice table, the initial concentration of the weak base given to us, and just like we set up for a weak acid, okay? So just remember though that one of the products is going to be hydroxide instead of hydronium ion. The value of Kb is likely small enough so that we can neglect Y when it's subtracted from the initial amount of weak base. Plugging the values from the ice table into the expression for Kb, and even though I believe it's safe to neglect the Y value when subtracted from the original concentration, I want to go ahead and keep it for now because I'm going to introduce you to something on the next slide called the 5% rule, and that's how you verify whether or not it's actually okay to neglect X or Y or whatever you call the variable. So I'm going to keep it in for now, and so I end up with a quadratic, but when I solve the quadratic, I get that the hydroxide concentration is 7.91 times 10 to the minus 3. Be very careful because since you have hydroxide ion concentration, it's a two-step calculation to get to pH. So one of the ways to get there is to take the POH first, and then remember that pH is simply 14 minus the POH. So as you would expect for a basic solution, you should have a pH greater than 7, and you do. All right, the 5% rule. How do you confirm whether or not it is okay to neglect X? Well, one of the things you can do is you can go ahead and neglect X and then solve for X and see whether the percentage of the X value you obtained by neglecting it over the concentration of the original value of the weak acid or weak base is less than or equal to 5%. If it is okay to have neglected X. So let's check the 5% rule for the problem we just did in the weak base, methylamine. So the value that we would have gotten for Y if we would have neglected X is, so in this case, let's see, Y would be 0.00812. And that compares to the Y we would have gotten, or Y we did get from the quadratic. Okay, I didn't notice until I started doing this lecture that I plugged in the value for the quadratic instead of what you would get by neglecting X. So now what we do is we do the 5% rule on the value. So we put in 0.00812 divided by 0.150 times 100, and that equals 5.4%. So what that tells us is it's not okay to neglect. It's really kind of on the borderline. But you can kind of see, 0.00812 is pretty far off from what we would have gotten from the quadratic, 0.00791. Not horrible, but Anyway, so if it doesn't pass the 5% rule, that means it was not okay to neglect X, which means you have to use the quadratic. And that is it for this lecture on weak acids and weak bases.